Bill Farrell, who will be talking about cold trapping of lunar polar crater volatiles.
All right, very good, thanks. I just want to mention that the way this started is there are two sort of different theories out there about cold trapping. One called cryo condensation, which has been applied at Mercury, and the LRO team is applying it at the moon. But there's also been this cryoabsorption picture, which the Survey team, the Vortice team at Georgia Tech and at APL have been working on. So in fact, what we did is we got together a consortium of groups from all of this, with sort of Dana Hurley having a professional wave function that sort of covered all of us here, and we're trying to make these two theories sort of come together and see where they overlap, or if they overlap at all. And of course, what we're talking about here is this official water. I call it frost. Maybe I shouldn't, but it's this a few percent mix in the regolith that is present. It was actually Dave Page suggested it should be at the surface and using temperature-based models back in 2011, and sure enough, LAMP saw something like this, the Lyman Alpha mapping project, where looking at the off and on bands, they were able to see a bump up with water where in the part of the band where it has a high reflectance, FUV reflectance, compared to part of the band that has a very low reflectance. Actually, it's about a factor of 100 for pure water. But even at 1% mixes of water, you still can see a bump up, a change. So they've inferred that Shackleton might have 2% icy regolith, Hayworth about 1% icy regolith. And in fact, this sort of off to on band ratio, they're about 25 nanometer bands, centered around 170 for the nanometers for the off band, and about 140 nanometers for the on band. That sort of now kind of used as an index. And Paul Hain last year actually had a great paper where he sort of calculated mapped these off and on bands within the polar craters and correlated them nicely. Found that they got more of these, you got higher values of these band ratios at lower temperatures. And of course, ratios around 2 or 3 or so representative of 1 or 2% water mixed with the regolith. He in fact also presented on-off ratios versus temperature at the crater level, and he found that actually it was a real nice correlation with the annual maximum temperature within the crater. The one exception is Shackleton, as it turns out, which tends to be UV bright across that whole band. So we want to talk a little bit about the exception here. So let me just first talk about the sort of the traditional view of cold trapping. This is cryocondensation, presented by Watson in '61. And basically, the idea is that the evaporation rate goes as roughly the pressure of the overlying gas, with that pressure varying as the exponential of the latent heat divided by the temperature. And it's really a sublimation process. It assumes that the gas is in equilibrium with the surface and now, and in fact, if you plot the log of this value, the log of this rate, as a function of 1 over t, you get this nice straight line. I think I'm losing my laser here. But you get this nice straight line here. And in fact, Zhang in 2009, Zhang and all defined a volatility temperature where basically you've slowed the evaporation rate to the rate where you lose 1 millimeter per billion years of water. And that, for water, that's about 110 degrees Kelvin. So this 110 degrees Kelvin is sort of used as a fiduciary. If you're above it, it assumes you're getting lost, and below it, you're stuck onto the surface. Although in reality, the model suggests that there's more of a, it's not quite as on-off as the way it's being used. It is a gas-driven process. I mean, really what happens is you're looking at this sublimation phase transition. In fact, you can use the Clausius-Capron equation and the ideal gas law to derive this exponential function with pressure. In fact, if you converted the latent heat to electron volts, and you look at this a little carefully down here.
Try that for the laser, but it won't advance.
Okay, you bet. Thank you. Let's see. Actually, is that going? Can you guys see that?
It's really faint, so I don't know.
All right. Oh, you're right. It is really faint. Yeah, okay. All right. So, you know, if you if you actually convert this to electron volts, what this really sort of looks like, it looks like a Maxwellian sort of expression where you're defining the probability of this ideal gas of having a molecule with enough energy to release a trapped bound molecule on the surface. And of course, as you lower the temperature, that probability gets lower and the evaporation rate drops. So this is all a gas-driven process. But in fact, you know, even though this might be great at Mercury where you got a block of ice, at the moon, it's not clear you have a full monolayer. In fact, you have this kind of fractional coverage where you might even have a mix of water, ice with the regolith. And in fact, you have a lot of the sorbent material, this sort of activated lunar regolith exposed to the free atoms that are coming in. And we know that, for example, in cryo pumps, you have a cryoabsorption process where you actually suck the gas out of the molecules right out of the gas long before you actually get a condensation. And actually, it's a function of how sticky the sorbent material is. So, and we're thinking that maybe this is what's going on in these lunar polar craters. That basically the sorbent is mostly exposed, and these sorbents have high trapping potentials, little pockets that can trap an incoming molecule. And this picture is different from the cryocondensation picture. So what we're really talking about here with cryoabsorption is really an atom-atom interatomic potential where the atom coming in can get trapped by the surface material. And in fact, the sticking time or the residency time is a function of how deep that trapping well is. So really, this works even if you just have an isolated molecule. You don't need any gas at all, because through one molecule at the surface, you're going to be dealing with these surface effects. And things like defects, impurities, they're actually not going to give you one activation energy value, but actually a broad range of activation energies. And Tom Orlando, I think, talked about this yesterday in his talk. So it's actually can take a statistical mechanics approach. And this is the way the APL Georgia Tech team has been doing their studies of temperature programmed desorption. Now, not that I want to kill people with a whole bunch of equations here, but I just want to point out that the formalism is very different between cryoabsorption and cryocondensation. You actually have a desorption rate that is defined by the Arrhenius equation here and the fractional coverage. And in fact, if you have a group of molecules, a handful of regolith, if you will, each of these sites are going to have different activation energies, so you can actually define a distribution of surface activation energies. So to get at the average of desorption rate, you actually have to integrate the Arrhenius equation over this distribution. So it becomes really a statistical mechanics problem. There's a nice paper by Barry that Poston used. It allows you to, in fact, invert. If you've got the desorption rate, you can invert to get the distribution function. And that's exactly, this is sort of what Tom showed yesterday. In fact, this actually almost looks identical to a slide, even though I didn't take it, even though he didn't give it to me. This is exactly, these are great plots here. Basically, what they did in the lab is they actually took a mature anthracite soil sample, put dose of water on it, and then warmed it up, and they found around 200, 220 degrees Kelvin, they were getting a peak in the water emission. And in fact, if you use that Barry inversion method, you find that peak corresponds to a peak in the activation energies at about 0.7 electron volts or so. So that's telling you the depth of those trapping wells. So about 10% of the surface seems to be covered with these, what Michael called these chemisorbed sites. Now, again, this kind of picture is very different from cryocondensation. And again, you're getting things going on well above this 110 degrees Kelvin volatile temperature. In fact, in the cryoabsorption frame of reference, you actually have a family of temperatures. What I apply here is residency time as a function of temperature. Residency time is over I believe, 14 decades here. Always a nice logarithmic plot. And really what this is the Arrhenius equation just re-expressed. And basically here are the TPD experiments done in the lab, right? Where you're looking at changes in the desorption on timescales of 100 to 1,000 seconds. And here's the 0.7 EV at 220 degrees Kelvin, sort of what Michael was seeing. But you can actually scale these back up, or ride them back up to what might be going on in the PSRs over tens of millions or a gig a year. And in fact, why this is important is if you look at the more traditional cryocondensation view, you'd be more or less limited to this red line. But in fact, if you have a set of activation energies, excuse me, on your surface above the above about 0.7 EV, you can actually get these to be trapped at much higher temperatures. And as, excuse me, and as an example of this, we actually did a Monte Carlo model of this, where we actually took a sort of forward model of this. We had a distribution of activation energies that we made up here with a center at 0.3 EV and a width of about 0.15 EV. And we found that around 100, 110 degrees Kelvin, we could boil those off. But in fact, if you added 10% of the post-enol cryo, chemi-absorb sites, you actually could upshift that condensation temperature or release temperature up to above 150 degrees Kelvin. Okay. And so to look at this in another way, here's the distribution, and here's the evolution of the distribution. We solved this using the Berry equation 8 here, out of their equation 8. If you ran it, if you sort of cooked the surface for 10 million years at these different temperatures, you find that at 50K you'd lose about half the distribution, or half that big core. But with the chemi-absorption sites that Poston and all found, you could actually have sites that go still present even up 150K. Whereas if you didn't have that those chemi-absorbed sites, they'd be all gone, and you actually get rid of the whole distribution up at 100 or 110K or so. So the bottom line is, we can't help wondering, Kaguya found, look at their NERIR system, found that in fact that the Shackleton is a northern-site rich. Now, northern-site is UV bright, but it also may contain a larger fraction of these chemi-absorb sites compared to these other craters. So it may be a better, more enhanced water trapping region. Again, this is a non-unique interpretation, but if you do the if you take this chemi-absorption point of view, as opposed to the if you take the absorption point of view rather than the cryo-condensation point of view, then it might make sense. So bottom line is, we can reinterpret or re-examine the lamp measurements using a cryo-absorption point of view. The tolling factor is U over T, and not just temperature alone. And I think that's about where I'm going to leave it here. Okay? Oh, thank you. Is this Vasa?
Excuse me. We have time for questions, but a little bit.
Quick question. So you identify Shackleton being special. A couple years ago, we published a paper using neutron orbital geochemistry that also shows that Shackleton is special bulk surficial hydrogen, and it's the only location within either the north or south polar region that seems consistent with surficial deposits. How would that connect to this?
Well, I mean, that would be, if it's richer in an orthositic sort of material, then it's just going to, it's going to retain the water, retain that H, and it could match up. How superficial were you? How deep were you going?
It's fast neutrons, so within the first 10 centimeters.
10 centimeters,
like
yeah. Well,
I'm
still
a few centimeters. It's definitely not subsurface, because we don't see the same signature with the epithermal neutrons. But
well, that would fit with this.
yeah.
That would be consistent.
Do we have any other questions? I think we can move on.
Okay. Thank you.